Okay, I gave you a few animations and some explanation last time in terms of volumes of revolution. We're going to go ahead and just jump right in with some examples. So let's go ahead and entertain y is equal to 4 negative x squared over 4 and y is equal to 2. Actually, I'll tell you what, let's go ahead and ignore this one real quick. Let's actually just go ahead and contemplate this one right here. Now, because of the way that it's constructed, it actually has a shape that looks something like this. 2, 3, 4. It has zeros at negative 4 and 4, and we should know that because all you have to do is multiply through by 4, and that would be 16 minus x squared. Or, of course, you could transform it into, factoring out a 4, into that. And of course, in this form, it's much easier to see the zeros. It obviously also has a y-intercept of positive 4. And so, and this is, of course, really hard to do like this. And this is generally the shape of that upside down parabola. Now let's say that I'm asked to take this area right here and I want to revolve it around that axis. Okay, and so just like the animations that I showed you, this area would be coming off of the paper and it would be swirling around so that any cross section that looks something like this, okay, this would be sort of a rectangular cross section, would have a corresponding sort of cross section down here, and it would be revolving around and forming sort of a cylindrical cross section. Okay, and you got to imagine this happening sort of all the way through here, so that you have a volume that kind of looks like a football, I would suppose. After you revolve it around there, it would sort of be footballish. The question, like I said, is how do we represent that cross section? Well, I happen to know that if I look at this cross section and I recognize that that right there, if I'm looking at the cross section, which is the cylinder, that's my R, okay? And R is always going to be f of x, or in this case we called it y, okay? It doesn't really matter. And we know that cylinders have a volume of pi r squared h. Now, when we turn that into an integral, we know that it's from a to b. We still have the pi. My radius is my function value, and my h, and this is because, in order to actually talk about a cylinder, usually we talk about a cylinder like this, but since ours are sideways, we recognize that height, the way that we usually talk about height, actually represents width. The infinitesimal width being r dx, okay? So here's my pi, here's my r squared, and here's my h. Well, in terms of this particular function, if I want this whole thing, I'm going from negative 4 to 4. So let's go ahead and negative 4 to 4 with the pi out in front. And I know that this winds up being 4 minus x squared over 4 squared dx. And in order to actually accomplish that, you either pop it into your calculator or you would actually have to FOIL out that into a trinomial. So it'd be a quasi-quadratic trinomial, and it'd have fractions and stuff like that in it, but that's really not too huge of a deal. You could actually, to make things a little bit easier on yourself, in recognizing the symmetry right here, is recognize that the volume of this half over here on this side of the y-axis is going to be identical to over here on the left side. So you could actually multiply by 2 pi and just run it from 0 to 4. And that would actually make your work a little bit easier, because anytime you have a polynomial integrand, you're going to have a polynomial integral, and plugging 0 into a polynomial gives you a very predictable result. It gives you 0. Okay. I'm not going to go ahead and figure this out. I'm not going to go ahead, on very few of these am I actually going to do the mechanics of actually doing the integral. I'm just going to show you, based upon what we know about the shape that we're shown and the area and the region that we're given and the axis around which we're spinning it, how do you actually set up the integral? The hard part is setting up the integral. The easy part, at this point at least, should be the mechanics behind actually accomplishing and discerning, evaluating that area after having set it up. Okay? Okay, so that would be it. Well, let's say, and this goes back to the original before I changed it and abbreviated it. Let's say it's not that whole area between -4 and 4. Let's say that I'm still given 4 minus x squared over 4, but I want the region bounded by that quadratic, that downward quadratic, and y is equal to 2. Well, that's the only problem with these gel pens, is they still are wet when you try to use your ruler. Sorry about that smudge, guys. I'm hoping that that's not too distracting. My OCD is going into overdrive, but I'll forge ahead bravely nonetheless. So here is our quadratic, and unfortunately that looks more like a semicircle than a quadratic, but you get the idea. And here is our linear. So somewhere in between -4 and 4, you get these points of intersection. Well, that actually should be relatively easy, and in order to find those limits of integration, we'll go ahead and we'll set these equal to each other and basically discern when they're equal. So let's multiply through by 4. We're going to get 16 minus x squared is equal to 8, or when I subtract 8 from both sides, I'm going to get 8 minus x squared, or x is equal to plus or minus 2 root 2. Now, 2 root 2 we could approximate. We don't have to. And we'll just go ahead and I think we'll just go ahead and put it in our limits of integration like that. But, for the sake of the future, I'll go ahead and remind you that that approximates to 2.828 because root 2 by itself approximates to 1.414. Okay, so we have our limits of integration, and like I said, if I'd drawn this more like a parabola and less like a semicircle, those points of intersection would have been inside 3 instead of looking like they're outside 3, so, not drawn to scale. So let's sort of put a box around this so it doesn't distract us as we move forward. And so we recognize the fact that we're going to be doing this, and I want to spin it around that same axis. Now, this one is just a little bit different because I'm not, basically the region that I'm revolving is not flush against the axis around which I'm revolving it. There's a gap right here, okay? So instead of having a cylindrical cross-section which looks like a disc, I'm going to have a cross-section that looks more like a washer, okay? Because I'm going to have this gap in here, okay? Now, if I were asking you, and this kind of looks something like this, okay? If I were to give you, sort of take an aside real quick, take a short excursus, and these kinds of problems are extremely prevalent on the SAT and ACT. They just love these. I have no idea why. If I ask you for the area of the shaded region, what would you say? Well, basically you would have to get this big radius, right? And then of course there would be this small radius. And you would basically want to get the area of the whole and then minus the area of the whole, right? So it would be pi r squared minus pi r squared. And that would be the area of the shaded region. Okay, well, what happens if I do the same thing and I add a third dimension to it, and I want to find the area formula, or the volume formula, for this disc, okay, this washer, Okay? Well, it's still the same thing. It's still the whole minus the whole, okay? And I'm still going to find a big radius and a small radius, big R and small r. It's just going to be pi r squared h minus pi r squared h, okay? Which, of course, you know, if you want to change it, becomes that. And the reason why I put the pi out here and the h out here is, remember that when you transform this into an integral, this winds up being pi times the integral a to b. Whatever your representation is, whatever your variable representation is for r squared, minus whatever your representation is for small r squared, and h, of course, is still our dx, okay? So this sort of becomes that, and this just sort of transfers down. Now, how does that actually bear out in terms of this particular problem that we've done? Well, here's the thing. Your radii will always be, okay, either the function minus the axis of revolution, or it will be the axis of revolution minus the function, depending on whether the axis is below the area that you're revolving or whether it's above the area. Well, let's actually just look at this just very intuitively. I recognize the fact that this right here is going to be my big R. Okay, no matter where it is, it's going to be big R, and that is basically this. That is my big R. My small r is going to be this gap right here. Okay, that's going to form the radius. Okay, that's going to form the radius of the whole, HOLE, whereas the function value is going to represent, and it's going to create the radius of the whole, WHOLE. So this right here is my small r. And basically, and the thing is that this one is variable. Notice that your big R is larger here than it's going to be right here. But your small r is still going to be 2, right? This is still 2. It's a constant. And this, however, is a little bit shorter, and it's still dependent upon that function value. So when you're trying to figure out the radii, both the small and the large, it's simple subtraction. Now the subtraction here is negligible because the axis of revolution is y is equal to 0. Adding 0, subtracting 0, it sort of is a non-issue, right? So what happens here is I have pi, okay, and then I go negative 2 root 2 to positive 2 root 2. Now here is where most people make a mistake. They won't put r squared minus r squared in the integrand. They'll accidentally put r minus r. So here's what I'm going to suggest. Every time you have a problem like this, I want you to make this little table. I want you to tell me that that is big R, and then I want you to go ahead and explicitly write out what r squared is. Not that you're not smart enough to figure that out on your own. It's just a visual reminder that this is what goes in the integrand, not this. Okay? R is equal to 2. R squared is equal to 4. This goes in the integrand, not this. Okay? And so what we have here is 4 minus x over 4 squared minus 4 dx. That right there is your integral. And of course, you know, using the same logic as last time, you could have gone 0 to 2 root 2 and just popped a 2 out in front because of the obvious symmetry of the region that you see in the picture right there. Okay? So I've done an example of the disk method. I've done an example of the washer method. In order to determine which is which, you simply have to ask yourself, the region that I am revolving, is it flush against the axis of revolution? If it's flush, there will be no gap right here. There will be no washer. It will be a disk. If it's not flush, then we're gonna have to deal with the 2 radii, and we're gonna have to deal with the washer method. Okay. Now I walked through these rather slowly and deliberately to make sure that we got those under our belt. In the next couple of videos, I'm going to be going a little bit faster, so be prepared for that. And then in the last couple of videos, I'm just going to take a couple of functions that I've already mapped out, and we're just going to see the intersecting regions of these several different functions, and we're going to just play with it and revolve different ones around different axes and stuff like that. So that ought to cut down on a little bit of the labor in terms of graphing and stuff like that. But that's sort of the MO as we're going to move forward in the next couple of videos. So please do keep that in mind and look forward to those.